Let's go back to looking at this idea of areas. Now what we saw, yesterday, was if the curve is above the axis, then we know it's going to give us a positive answer to the integral. Whereas if it's below, it'll give us a negative answer. So if I've got a question where, say, I wanted to work out this area, I'm going to have a problem because the integral is not going to give me the answer, because it'll get the positive amount and then the negative amount will be the bottom, and I'll get a smaller amount. So I'm going to need to break it up into what's above, what's below, work out the different areas and then add them together. So area A to B would be a positive amount, area 1. Area 2 from B to C, that's below the axis, so that would be a negative amount. So to say, if I was to just go from A to C, I'm not going to get the right answer. So I've got to break it up into two integrals. So how do we find the below? Well, we know the below is a negative amount, so I could simply say, oh well, the area therefore would be the negative of that integral. And that'll make it a positive number, and that would be the area. I suppose I could use absolute value. I could say, oh, what's the absolute value of the integral? Again, that would give me a positive number. The other way I could do it is swap the numbers around. Remember, when we swap the numbers around, we change the sign. So if it's below, instead of going from B to C, I could go from C to B. So that's a third way I could set the problem up. So let's have a look at this, basic one of a cubic going from -1 to 1. And if I just did an integral, the answer is going to be 0, of course, because of symmetry with the odd function. The area below would be the same as the area above. So they would cancel out and give 0. So I could do it this way. I could say, okay, well, look, the area below will be negative. So I'll make it negative from -1 to 0, but positive from 0 to 1. And then we just integrate as normal, add 1 to the power over the power, substitute into the two different things, and there's my answer of a half. Of course, I could have used the symmetry. Because I'm finding area rather than integral, though, I know the answer is not going to be 0. I could simply say, oh, well, I know it's going to be twice from 0 to 1, because those areas would be the same. And so in that case, I'd just integrate it once, and again, I come up with the same answer. That one, of course, I could do because of the symmetry of the odd function. Obviously, not all curves are going to work like that. There's got to be an odd function for that to work. Well, let's look at something like this, where it's not an odd function, it's not an even function either for that matter. It's just some random polynomial, which I've got factorised up there. So we've got a bit that's above and a bit that's below. So I know, well, if I expand that whole thing out, it becomes x cubed plus 3x squared plus 2x. The bit that's above, I'll go from -2 to -1. The bit that's below, I'll do the negative of -1 to 0. If you're observant, you'll notice I've changed it slightly there. I actually like the swapping the limits around. See how I've changed it to a positive when I integrate it, but my limits have changed from 0 to -1. And the reason I like that is because now for both of these brackets, the number on the top is the same. They're both -1. So I don't have to substitute negative in twice. I'll just work out what it is when I substitute in -1 and times it by 2, because I'm going to substitute it in 2 times. So now I can say, well, look, it's 2 lots when I substitute in -1, but then I'll take away when I substitute in -2, and I'll also take away when I substitute in 0, because they're the ones that are on the bottom. And it's just a little bit less work to do, I suppose. So there's a half of it. What about if we're going to the y-axis instead of the x-axis? So some sort of area like this. Well, in this case, I'm going to rearrange the equation to make x the subject, because, and you'll like this, if we're going to go to the x-axis, we want it in terms of x. If we're going to go to the y-axis, we want it in terms of y, so we want it the y. Okay? So we make it a function of y, because then I can work in, possibly we're going to have to work out the y values then, because I'm going to substitute in the y values, not the x values. And there's my area. You'll notice it's the integral the y, because we're going to the y-axis, as opposed to before where it was integral dx, because we were going to dx axis. See? Sometimes the English language works for us. Well, just the abuse of the English language works for us. All right, let's do an example where we're going to the y-axis. So it's inside my parabola, but I'm interested just going from, well, that would be the point 1, 1, and the point 2, what would that y value be? 2 to the power of 4, which is, of course, 16 would be that y value. Okay. First thing I do, rearrange the equation to make y d subject, because we're doing it with respect to the y d subject. Okay, there's my integral. Notice the limits have changed. They're now in terms of y. Y to the power of quarter, dy. Add 1 to the power over the power. We get 5 on 4, turn it upside down, 4 on 5. Substitute in. So basically it's the same. It's just that we're going to a different axis. Now, this is where the bit you're going to love. Sketching a diagram really helps. I know how you love doing your diagrams. You know, you spend so much time making them look neat and proper. And so when you see the diagram, then it can be like very clear what area you're talking about. What happens if we're between two curves? So here's random function 1, which I've cleverly called function x. Here's random function 2, which I've called g of x. We're going to find the area between these two curves. So that section in there. Finding the point of intersection will come in handy, because then I'll know where I'm going from. And clearly I think we can see there, well, if I just found the area under the red curve, and I found the area under the blue curve and subtracted, I've got my answer. So it'll be the integral of function x dx from a to b minus g of x dx from a to b. But remember, we have a rule that says we can combine that into one integral. And so it becomes the integral of the top one minus the bottom one, basically. And again, that's why a diagram is good, because you'll know which one's on top. If you get it the wrong way around, what will happen? You'll get the negative answer instead of the positive answer. Yeah. All right, we're going to find the area enclosed between x to the power of 5 and just the straight line y equals x in the positive quadrant. So let's draw a picture, see what we're talking about. You'll notice there's two sections, but we're only interested in the one in the positive quadrant. So we just want that bit in there. Need to know where they meet. Not quite sure. X to the 5 equals x. So x to the 5 minus x equals 0. I can factorise that. And eventually we get the 3 points of intersection. So the top one minus the bottom one. The line is on top. So it'll be x minus x to the power of 5. We're going from 0 to 1. Add 1 to the power over the power. Substitute in. There's our answer, 1/3 a unit squared. Let's have a look at a, well, fairly old HSC question now. Comes from a two-unit paper, and they were quite nice. They gave us a lot of hints in this question. This is the graph of y equals x minus 4. There's the straight line. And x squared minus 4x is the parabola. And they've told us it intersects at the points 4, 0 and A. They haven't given us the coordinates for A. The first part of the question was, find the coordinates of A. Okay, well, we'll solve them simultaneously. That's how we find points of intersection. So, x minus 4 equals x squared minus 4x. Multiply together, give 4. Add together, give minus 5. Minus 4 and minus 1. 1 or 4, well, they've already told us the other one's 4, 0. Therefore, A must be the one where x is 1. So therefore, A, the y coordinate when we sub in, turns out to be -3. Find the area of the shaded region, so in between the two curves, x squared minus 4x and x minus 4. We got the point of intersection. So basically, we just have to do the top minus the bottom. The line was on top, minus the parabola was on bottom. X minus 4 minus x squared minus 4x, going between our points of intersection, 1 to 4. And there we go, just tidying that up, minus x squared plus 5x minus 4. Add 1 to the power over the power. Substitute in. Whee, there we go. 9 on 2. That's not a half. That's 9 halves. 4.5 even. Oh, here is an interesting one. We've got a circle and a parabola. So shaded region, bounded by circle, radius 2. They haven't given us the equation for the circle though, but we know what that is. X squared plus y squared is 4, by the way, in case you're wondering. Parabola, x squared minus 3x plus 2. Find the area of the shaded region. Now we've got to be really careful here, because notice it doesn't include the little bit down the bottom here. So I can't simply say the circle minus the parabola between the 2 points of intersection. If the boundaries change, then you split the integral up into 2 different integrals. So I'm going to break it up into 2 areas. There we go. There's the red line. So on the left-hand side of the red line, I'll go circle minus parabola. On the right-hand side, it's simply circle to the x-axis. So just a standard integration problem, not an area between 2 curves. Okay, so there's our problem. But I'm not going to do that. I'm going to find that area and subtract it from a quarter of a circle. See, if you've got the picture, sometimes you can find easier ways to solve a problem. That would have taken a bit of effort, that other one, when you think about it. I would have had to find points of intersection and all sorts of things. Here, I can just do one little integration, subtract it from a quarter of a circle. So, a quarter of pi r squared minus, and we just want simply the area under the parabola going from 0 to 1. Add 1 to the power over the power. And there's our final answer, pi minus 5/6 units squared. All right, so 11E and 11F.